All right, folks, let's go ahead and get started. First things first, in a lot of my lectures, you're going to see something called a flashcard moment. It's just for the folks who like to use a Leitner technique, which means that you have a bunch of flashcards to help you understand information. What I would like you to do, if you see a flashcard moment and you are that student, is to take the front of the flashcard and write something general, like, for example, math. And on the back of the flashcard, you would write an example or even your definition of what matter means. The main goal of our course is to make sure that you know how you understand this information in your own voice and in your own words. You're going to hear information from me. You're going to see information from the textbook as you're reading and comprehending. And guess what? A lot of times, all that's going to come at you a lot. We want to make sure you have your own voice for the information. That's how you're going to be able to remember a lot of this stuff. So just keep that in mind as you're going along. Okay, folks? Remember, our main goal is to understand the chemical level of organization. And that means we have to understand what chemistry means. So chemistry, of course, the Y here is pertaining to, and the chemist portion is talking about chemicals. Chemistry is the study of the structure of matter. Now, why are we focused on matter first and not just jumping into chemicals? Because chemicals are made of matter. And what is matter? Matter is going to be anything that takes up space and has a mass. So that means it could be a piece of paper. It could be a shoe, right? I don't know why I'm drawing a shoe, but it could be a shoe. It could be a paper clip, anything that can take up space. And so when we're talking about space, we're talking about volume. So for example, if you're standing up in a room, you're taking up space in that particular area that you're standing, in a particular volume that you're standing in that room, okay? And of course, you would have mass. All of matter is going to have mass, and that just really means the quantity of matter that you have. So for a human being, what is the quantity of matter that actually exists? That will be your mass. What's the quantity of matter for this shoe? That will be its mass. The amount of matter for this piece of paper, that will be the mass, right? And some folks will be like, well, isn't mass and weight the same thing? The answer is no, folks. If you're thinking about mass, it's just telling you the amount of matter you have for that particular thing you're focused on. Human being, shoe, paper. Weight is going to include gravity and the force of gravity on that mass. That's why when some folks say, okay, what is my weight on Earth versus your weight on the moon? They're going to be two different things based on the gravitational force that's going to be applied to that mass. But if I'm just talking about the mass in general, that's what I mean by mass when it comes to matter, okay? Now, if we're talking about anything that takes up space and has mass, there's different states of matter that we can focus on as well. We have solids, so we can think of like ice cubes. I mean, of course, that piece of paper is a solid as well. We have liquids like water. And then we have gas, like oxygen gas that we breathe, or CO2 gas that we exhale. All these things are different types of matter. But again, they have a mass and they take up space. So that's where that definition is coming. Now, you might want to say, okay, it's great to know about matter, but how do we make matter work for us? How do we make matter move in some kind of way? If I have this solid ice cube, how does this ice cube move if I had it in my hand? Well, I would have to put in work. I would have to use the force of my hand to throw the ice cubes, for example, right? And so the capacity to do work or put that matter into motion is what energy is. Okay, yes, it's a crude example. As you go up higher in chemistry and you learn thermodynamics, you'll get into more details about energy. But for us, this is good enough. Now, there's two overall forms of energy that we have. One is going to be kinetic, or the energy when it comes to movement, and one is going to be potential, or the energy that is stored. Now, the beauty of energy is that it can be converted. It's never just lost or destroyed, right? It cannot be created or destroyed. It can only be transformed from one form to another. So, for example, if I have potential energy, like potential energy that's stored in like a muffin, okay? Guess what? That muffin has a bunch of chemicals in it, and each of those chemicals have certain bonds attaching to them that holds energy. Now, when I start chewing and chewing and chewing and eating, that energy gets broken down. And if that energy gets broken down, then I can use it for things like moving my bicep, okay, or walking. And that will make that potential energy turn into kinetic energy, which is the beauty of understanding energy in that way, okay? Now, the first law of energy conversion, you can also say, or energy conservation, you can also say first law of thermodynamics, is that energy cannot be created or destroyed, only transformed from one form to another. So we get to just keep transforming it from one thing to another, one thing to another, one thing to another. How does that apply to human beings? Well, everything we do is about chemical reactions, which we're going to talk about later on. And these chemical reactions help us with transforming types of energy, or even producing types of energy, okay? Now let's think of one large chemical reaction that's probably one of the most important ones we get to see. And when we talk about metabolism in chapter 4, we'll see this again, and that's going to be cell respiration. not respiration like breathing, but cellular respiration. How do we make energy so that we can use it, or usable energy that we can actually have for all these physiological processes that we talk about? So, for example, we're going to start with some potential energy here, like food. Let's say we're eating some, what they got over here? Seafood boiled, some salad. I don't know, but I see a limit at least. So this is all of our chemical energy. It has carbohydrates, fats, all those macromolecules that we briefly spoke of in the beginning. And we're going to be eating all that stuff. And then it's going to get broken down in our body, and specifically our cells, into glucose. And glucose, as we know, is sugar. It's a carbohydrate. So let's focus on carbohydrates. Fats have their own way of being broken down. Proteins have their own way of being broken down. And again, in chapter 24, we get to see those details. We're going to talk about sugars from carbohydrates. So we go ahead and eat some bread or whatever else they have for us, or some potatoes here, and it's going to form glucose. And based on the oxygen or the air we breathe and the oxygen that's within that air, this glucose and oxygen come together to go through a series of a bunch of chemical reactions to form two products, CO2 and water. One product they're not showing you is that it also forms ATP, adenosine triphosphate. And it literally is a nucleotide that has a bunch of energy attached to these three phosphate groups. And the beauty of that is that one of those phosphate groups can break off, release energy, and be used to push forward many chemical reactions in the body. Okay? And when you have a bunch of chemical reactions in the body, meaning every chemical reaction you have, all the chemical reactions in the body is called your metabolism. So we get to learn a lot of details about this, right? And I can keep going on because I do like chemistry, but I just want to be able to kind of keep this in your head to get you started with all this stuff. Okay? Now, another thing that happens, let me go ahead and erase this. Another thing that happens when it comes to chemical reactions and cell respiration specifically is that you also can have energy released as heat, or of course, thermal energy. And think about it, a lot of chemical reactions that we have, most chemical reactions actually are going to release heat in some capacity. For us, it's a benefit because the excess heat that's going to be utilized can be helping us with regulating our body temperature. That's where thermal regulation comes in. Now, you might be asking, why is heat involved in the first place? Well, guess what? Chemical reactions aren't perfect. They're not always going to just perfectly create the products that you're looking for. A lot of times you have insufficient conversions. Sometimes the molecules don't collide enough with enough energy to actually form the products. And so all of that excess gets released as heat. We do see that as well. Okay? But the beauty of cell respiration overall is that it does form this usable energy that we can use to help put matter into motion. Now, there's different types of energy. We have the chemical energy that's stored in bonds. Usually it's just like stored in foods, like we talked about with our muffin. Electrical energy, which is like the movement of charged particles. Think of electrical currents, again, help to understand the physiology of the heart, for example. We have mechanical energy, which helps move matter, like I was talking about moving your biceps or, running or walking. And then we have radiant energy. Really, it's called electromagnetic energy. And these are waves or particles of light, UV, X-rays, gamma rays, microwaves, all that cool stuff. That's actually energy as well. And we use that energy in a lot of ways. We use microwaves, as we all know, to heat up food, right? We definitely use UV rays and X-rays, and we definitely use light so we can actually see things around us with the visible light spectrum. So we have a lot of little things that we definitely use for this as well. Okay? Now let's think about this. If we have glucose that we're forming that's going to help us form ATP, that's great. We know it can actually form heat or thermal energy, that's great. But we also have it to where, what if you have a bunch of glucose that maybe you're just eating a little bit too much and you don't need the excess glucose? Well, guess what? That's going to be stored as fat. Okay? And you can use this for insulation, et cetera, et cetera. A lot of times it's stored as glycogen. You can have it stored in your muscles as well. And we'll see that as we go along. That's the beauty of this chapter. It's just so much information about us just getting the details down of what's going on, and then we get to build upon it. Okay? Let me go back really quick. Because I'm like, if you are going to be using a flashcard moment, how would you use this? Well, I would say matter and energy, or I would just have one flashcard for matter, one flashcard for energy. And on the back of matter, I would talk about the states of matter or just come up with my own definition in my own words. And then for energy on the back, I will do types of energy, have an example like the cell respiration here, and kinetic and potential. It's just up to you. Okay, folks? You just keep that in mind. Now let's move on. All right, we know that matter is going to be anything that takes up space and has a mass. We know that matter, if we want to use it in some kind of way or push matter into motion, we have to have energy associated. But what is matter made of? Okay, so it's like one of those situations like we have matter, what is matter made of? Now we know what matter is made of, what's that made of? So it's like a lot of little trickling down we have to do. All matter that we're going to be focused on is composed of atoms. Okay, so composed of atoms. Let's keep that in mind. And these atoms are made of subatomic particles. So sub means below, and atomic means a part of the atom. So it's saying a tiny thing below the largeness of whatever the atom is. Atoms are super small, but we're talking about this in context. So this atom, if I just have to draw an atom here, is made of something smaller. And there's 3 different subatomic particles that's smaller than the atom itself. That's going to be protons, neutrons, and electrons. Now, of course, what's going to, if the atom is the smallest unit of matter, and it's not the smallest unit of matter if you're talking about subatomic particles, it's really the smallest unit of matter that's going to keep all the properties that make it what it is, okay? And if atoms are these small units, then some folks might say, well, why do we have the periodic table? Why don't we have the periodic table? Some people might know what it is, some people might not. The periodic table is how we organize atoms. So if you have a substance that's made of one type of atom, okay? So you have a substance like oxygen, the air we breathe, that's made of oxygen atoms, okay? And because that substance is only made of one type of atom, we call it an element. And these elements are organized on a periodic table. So a wonderful chemist, Dmitry Mendeleev, he came together and he was one of the first people to create the organization of the periodic table. And that's going to help us understand everything that we need to know when it comes to looking at this table and being able to pull information from it. What information can we pull from this table? We can pull how many protons, how many neutrons, and how many electrons each of these atoms or elements, which are made of atoms, had at any moment. So we can just choose anything. I'm choosing carbon here. I'm also going to choose oxygen just for an example. We can choose these two. We can start pulling that information. Let's go ahead and do that. All right, so I got my carbon, I got my oxygen. Let's go ahead and pull these out. Here we have here. Now, if I was to take this from the periodic table, there's going to be names and labels and little numbers, and we need to figure out what that means. So first things first, you're going to see the chemical symbol. We have that here. That's the chemical symbol, and apologize for my messy handwriting. Then you're going to have the chemical name. So C is for carbon, O is for oxygen. And then you're going to have 2 numbers. The number at the top or above the actual chemical symbol is called the atomic number. And the one at the bottom is called the average atomic mass. Now, the beauty of the atomic number is that it gives you the identity of the atom, any atom you want. And as you can see, if you look at the periodic table, let me scroll back, every single element has its own specific atomic number. That's because every element has a specific amount of protons that are going to be associated with it. Okay, so atomic number gives you the identity of the atom, and it gives you the number of protons for that atom. We're going to talk about that next. Atomic mass, or the average atomic mass, is going to give you the number of protons and neutrons of that particular atom. Now, folks will be like, okay, you're giving us new verbiage. We have protons and neutrons. How does this all connect? Well, let's go ahead and talk about it. We already said that atoms are made of things that are smaller, which are called subatomic particles. So an atom, if we were to draw what it looks like, it's hard because we really should be drawing a 3D shape, where I'm going to be showing you this in 2D. Okay, so it has its own nucleus, and that says nucleus, and then it is surrounded by larger electron clouds. Okay, so we have our electron clouds here. These are electron clouds. And there's 3 particles that make up an actual atom. We have electrons, protons, and neutrons. And you'll see how I write it. I put E and then a little minus sign because electrons are negatively charged. and then I put a P for proton, and I put a plus sign because these are positively charged, and then an N for neutron, and I put a little 0 because these are neutral. They have no charge attached to it. Okay? Now, when it comes to an atom has a specific mass based on the nucleus itself. And the nucleus is made of protons and neutrons. And surrounding the nucleus is going to be specific amounts of electrons. So when you're looking at carbon and you're seeing the average atomic mass, this average atomic mass is coming from the number of protons and neutrons in the nucleus itself. And because of that, that's where you get most of the actual mass for the atom from. Okay, folks? So people might be saying, well, what about the electrons? The electrons do have mass associated with them. It's just smaller, way smaller than what the protons and neutrons are. So you look at the weight or the mass of it as negligible. Okay, folks? So keep that in mind. All right, so then the question becomes, how can we use the periodic table of elements, or these little boxes that we see, to help us figure out the number of protons, number of electrons, and number of neutrons for a particular atom? So let's focus on carbon. Again, we know that this is going to be the number of protons. We know that this is going to be the number of protons and neutrons. Neutron, erase that. Protons and neutrons. And we can use this to help us basically do subtraction to help us figure out what the number of neutrons are. So let's go ahead and figure out how we'll do that. But first, let's go ahead and write the number of protons. That's always going to be the easiest number to get because it's right here on the periodic table. So for oxygen, I can say the number of protons over here is equal to 8. It's right there. Now the number of neutrons is a little bit different, right? 0 there. We know that the average atomic mass is the number of protons and neutrons combined, and we know the number of protons, so we can take this number, 12.0 minus 6, and we can get the number of neutrons. Now you see how this says 6.01? We cannot have 6.01 worth of a neutron. So we just make the number of neutrons 6. We just keep it as whole numbers. We don't need the extra decimals. Okay? Same thing over here. We have 15.99 minus 8. Okay? And when you have your 15.99 minus 8, again, one of the main things that we do is we round up. We will round this 15 up to 16.00 minus 8.00, and then we'll get, again, 8 neutrons. Okay? 8 neutrons here. Now the question becomes, what about the number of electrons? That's one thing we haven't spoke about. Well, here's the beauty of the periodic table. When you look at the periodic table, you don't see anything with a charge. A charge means, like, say it's charged with a +1 or it has a -2. You see nothing with the charge on this periodic table. That means every element here is considered neutral. And because of that, if we go back and we look at our understanding of protons and electrons, we see that protons are positively charged, electrons are negatively charged. So if I have 5 positive charges and I have 5 negative charges, that'll give me 0 or neutral. And that's how we kind of get around it when it comes to the electron amount for the periodic table. So for example, if I have 6 protons, that's going to give me 6 positive charges. And in order to get it to be neutral or 0, I need 6 negative charges. Same thing over here. If I have 8 protons, then I'm going to need 8 negative charges for electrons in order to get to a neutral element on the periodic table. So 8 minus 8 is 0. Okay, folks? So you can be seeing one of these. It could be like a little freebie question that you may see on an exam. So just keep that in mind. Let me go ahead and just write this better. So again, 6 protons, you can even write it this way, 6 electrons, 6 neutrons. You don't have to put the charges if you don't want. Over here, 8 protons, 8 electrons, 8 neutrons. Now, it doesn't always look this perfect, right? But just remember, it's about whole numbers. So you can't have 15.99 worth of protons and neutrons. You want to round it up. And when we do our calculations, or if you ever have to do calculation in chemistry, a lot of times they just allow us to use the full number. But if we're talking about subatomic particles, you definitely want to round up. Okay, folks? So just keep that in mind. Atoms are really the building blocks of elements. You can look at it that way as well. You want to be able to have your flashcard and put, atomic number or atomic mass, or I would even just draw one of these elements, maybe vanadium here. And I would just go ahead on the back and put the number of electrons, protons, and neutrons for it.